Welcome back to the deep dive. Today we're doing something a bit different. We're not just looking at the final picture of relativity theory.
No, we're actually trying to get inside the head of the person who built it.
Exactly. Right at this really pivotal moment in physics history, we've got this lecture Albert Einstein gave in Gothenburg, Sweden, July 1923.
And the timing there is just crucial, isn't it? This is, what, 8 years after general relativity was properly formulated?
Yeah, and he'd just gotten the Nobel Prize, finally. But this talk, it wasn't him taking a victory lap. Not at all.
Far from it. It reads like a really tough self-assessment. He's already pointing out the cracks, the compromises.
The huge unsolved problems he saw still sitting right at the foundation of physics.
Yeah, absolutely.
Okay, so let's dig into this. Our mission for this deep dive is to kind of retrace Einstein's whole thought process, how he got from classical physics, Newton and all that,
Through special relativity.
and then landed on general relativity. And we need to frame it using these two sort of guiding principles that he kept coming back to.
Yes. These two ideas really drove everything for him, didn't they? The first one is the big one, the physical relativity problem.
Which is basically asking, does nature play favorites? Are there special preferred states of motion out there in the universe?
Mm-hmm. And his goal, ultimately, was to say no. Absolutely not.
And the second idea, which sounds maybe a bit more philosophical, but it's critical for how he did science, it's this stipulation of meaning.
Right, the epistemological side. This idea that concepts, distinctions, they're only really legitimate in physics if you can tie them to something you can actually observe, something unambiguous.
If you can't measure it, if it's just an idea floating around.
Then it's suspect. Logically weak. It probably needs to go.
That's the key insight, isn't it? We're going to see how he uses that stipulation, like you said, almost like a philosophical sledgehammer.
Yeah, to break down the foundations of classical physics, which he felt were really shaky.
So our goal for you listening is to really step inside that struggle, to understand why these revolutions had to happen, not just the famous results like EMC-ETO or curved space-time.
But the logical necessity behind them. What forced his hand, really?
Okay, let's start where he started. Section 1. Applying these two big ideas to the physics that ruled for centuries classical mechanics. So, first question. Does classical mechanics think there are preferred states of motion?
Oh, absolutely. Based on Newton, the answer is a clear, straightforward yes.
And those preferred states are the famous inertial frames.
Exactly. An inertial frame is defined, as any setup, any coordinate system, where if you have an object with no forces acting on it,
It just floats there, or moves at a constant speed in a straight line, no acceleration.
right, it's the place where Galileo's law of inertia just works perfectly. That's the definition.
Okay, but that definition itself, it kind of creates a problem, doesn't it? Because if you find one inertial frame,
You found infinite ones. Anything moving uniformly, without acceleration, relative to that first one, is also an inertial frame.
so classical physics ends up saying there's this whole infinite family of preferred states of motion. They're all equivalent to each other.
Mm-hmm. But they're all somehow better or more fundamental than, say, a spinning frame or an accelerating one.
Which sounds kind of neat, but it's unsatisfying, right? It doesn't really explain why. Why are these frames special?
Exactly. It doesn't give a physical reason. It just states it as part of the laws.
And this is where the second pillar, the stipulation of meaning, comes crashing in. How does this whole inertial frame idea fail that test?
Well, it fails pretty badly, actually, on two main counts. First, the whole idea of motion itself.
Okay.
Einstein's point is that motion fundamentally can only ever be understood as the relative motion between physical bodies.
Yeah.
You see something move relative to something else.
Right, you can't see something move relative to nothing.
Precisely. Yet classical mechanics sets up its fundamental laws based on motion relative to this coordinate system, which often gets treated as something purely imaginary.
Oh, so you're talking about Newton's idea of absolute space, this invisible grid that everything is really moving against.
That's the ghost in the machine, yes. It's the ultimate example of a concept you can't tie to an unambiguous observable fact. You can't see it, you can't measure it, you can't interact with it.
So it fails the stipulation of meaning right there.
Big time. But, okay, physicists weren't naive. They tried to make it more concrete. They said, all right, forget absolute space. In the lab, we'll use a practically rigid body as our coordinate system. Like a big metal frame or really sturdy measuring rods.
Makes sense, something tangible.
But Einstein argues that's also flawed.
Why? Because nothing's perfectly rigid.
Exactly. The whole concept of a perfectly rigid body is just an idealization,
Huh.
an approximation we find in nature, but never perfectly. And here's the kicker, the real logical problem. You're using this idea of a rigid body to define the fundamental laws of space and motion. But then, later on, you try to explain what a rigid body is using atomic theory.
Using the very laws you derive from the rigid body concept in the first place.
You got it. It's completely circular. It's well, a logically unjustifiable deficiency, as he put it, right at the heart of the theory.
Wow. That's some serious self-critique of the physics he inherited. He's really pulling back the curtain on how messy the foundations were.
He really is. And this mess extends to how motion itself is treated. Classical mechanics says velocity is relative, right? Your speed depends on which inertial frame you pick.
Yeah, that seems straightforward.
It insists that acceleration and rotation are absolute. If you're in a car and it speeds up, you feel that pushback in your seat. That feeling, that acceleration, is considered absolutely real, independent of which inertial frame you started measuring from.
Okay, but wait. If all motion is just relative motion between bodies, why should acceleration suddenly be absolute? Relative to what? That invisible absolute space again.
That's the core tension. The deep dissatisfaction. It feels inconsistent.
And this leads to the final nail in the coffin for the classical inertial frame, the thing that really opens the door for general relativity.
Yes. Because think about the definition again. An inertial frame is where a force-free material point experiences no acceleration.
Okay.
But how do we know for sure that a point is truly force-free?
I guess we can't. We'd have to assume we already know all the forces acting on it, which is kind of what we're trying to figure out with the laws of motion in the first place.
Exactly. It's the ultimate circularity. There's no independent experimental way to confirm a point is truly force-free without already assuming the laws you're trying to establish using that frame.
So the very definition is built on sand.
Einstein calls it vague and weak.
Yeah.
And he explicitly says this deficiency, this logical hole, is what ultimately necessitates the general theory of relativity.
So, to sum up Section 1, classical physics fails on both counts. It picks preferred frames, violating the physical relativity problem, and its core concepts, absolute space, the inertial frame, the rigid body, they all fail the stipulation of meaning because they aren't based on solid observable facts.
A pretty damning critique. The foundations were definitely rotten.
Okay, so the old house needed serious renovation, maybe even demolition. But before GR completely rebuilt it, there was this crucial intermediate step, special relativity or SRT.
Right, and SRT wasn't about tearing everything down initially. It was more like an urgent patch job, really.
Driven by what mainly?
Driven primarily by the huge success of Maxwell and Lorentz's theory of electromagnetism. Physics had these two great pillars, mechanics and electromagnetism, and they didn't quite fit together properly. SRT was the adaptation needed to make them compatible.
But it didn't throw everything out from classical physics.
No, not at all. It actually kept some of the core classical assumptions. Things like Euclidean geometry space being flat, basically.
Yeah.
And it still relied on the concept of the inertial frame and the law of inertia.
But it added two new, absolutely non-negotiable rules on top.
Two key postulates. The first is the special relativity principle.
Which says?
It says that the laws of physics are exactly the same in all inertial frames. It doesn't matter if you're sitting still or cruising at a constant velocity. The rules are identical. You can't do an experiment inside your sealed spaceship to tell if you're moving uniformly or not.
Okay, that sounds like an extension of the classical idea of relativity.
It is, but the second postulate is the really radical one, based on how light behaves, the light principle.
The speed of light in a vacuum is constant, always, for.
Always these dollars, for everyone. No matter how fast you're moving towards the light source or away from it, or how fast the source is moving, you always measure the same speed.
Right. And trying to make those two ideas, everyone's frame is equally valid, and the speed of light is the same for everyone trying to make them both true at the same time, that requires a massive sacrifice.
Huge. Arguably the biggest conceptual leap of the early 20th century. You have to give up the idea of absolute time.
Yeah. For hundreds of years, time was just time, ticking away the same for everybody everywhere in the universe, like a universal clock.
Before SR, the assumption was you could synchronize two clocks, move one around however you like, bring it back, and they'd still show the same time elapsed.
But SR completely demolishes that.
Utterly. Because if the speed of light has to be constant for everyone, then time itself must stretch or shrink depending on your motion. Time becomes relative.
So each inertial frame gets its own specific time, measured by clocks that are just sitting still within that frame.
Exactly. And this is where the idea of simultaneity breaks down. Events that look simultaneous in one frame might happen at different times in another frame. There's no universal now.
And the math that makes this work, that connects space and time in this new way, are the Lorentz transformations.
Yes. And critically, Einstein emphasized these aren't just mathematical tricks to make the equations work out. They describe the physical reality that results from accepting those two postulates.
And they lead to these really counterintuitive but experimentally verified consequences of relative motion.
Right, the famous ones. You get Lorentz contraction objects in motion appear shorter along their direction of travel when measured by someone in a different frame.
And time dilation clocks that are moving tick slower relative to stationary clocks.
And these aren't just illusions, like things looking smaller far away. They're actual effects on the geometry of space-time itself, baked into the fabric of reality by the constancy of light speed.
It's easy to forget just how radical that was. Not just fiddling with physics equations, but changing our fundamental understanding of space and time. They're not separate things anymore. They're interwoven. And how they weave depends on how you're moving.
And the successes were undeniable. SRT beautifully reconciled mechanics with electricity and magnetism. It simplified electrodynamics. And of course, it led to the understanding that mass and energy are related.
EMC2 to Thousers, the big one.
The big one. Though that specific equation isn't explicitly in this lecture, the underlying principle of mass-energy equivalence is a direct consequence, and it enforced that epistemological clarity, basing concepts on what could, in principle, be measured.
So huge successes, unified physics, explained light, gave us mass energy. But even with all that, in 1923, Einstein looked back at SRT and said it was not entirely satisfactory. Why? What was still wrong?
The core failure, in his view, was that it was still special relativity, not general relativity. It hadn't actually fixed the fundamental logical flaw inherited from classical mechanics.
Which was?
It still picked favorites. It still gave preferential treatment to certain states of motion, that infinite family of inertial frames, over all the accelerated or rotating ones.
Ah, okay, so it got rid of the idea of one absolute frame, like the old luminiferous ether.
Yeah, that was gone.
But it replaced it with this infinite set of equally preferred inertial frames. It still violated that deep desire to have no preferred states of motion at all.
Exactly. And Einstein actually found this more troubling, philosophically, than the old ether idea.
Really? Why?
Because the ether theory, even though it turned out to be wrong, at least tried to offer a physical reason for why one frame, the one at rest relative to the ether, might be special. SRT offered no real justification at all for why inertial frames should be privileged. It just built that preference into the structure of its laws.
That was just arbitrary.
Felt arbitrary, yes.
Yeah.
This vagueness in the definition of the inertial frame, as he put it, this lack of a deep reason for their special status, meant the job wasn't finished. The revolution was incomplete.
And it's tackling that lingering arbitrariness, that lack of a reason, combined with a key empirical fact that finally pushes him over the edge into general relativity. Okay, so special relativity fixed a lot, but it still had this leftover problem of preferred inertial frames. The bridge to general relativity, the insight that finally gets rid of all preferred motion, comes from a well-known empirical fact: the equality of inertial and heavy mass.
Right, the equivalence principle. Let's unpack why this specific observation is so absolutely critical.
Okay, so inertial mass, that's how much something resists being pushed, right? The M in FMA.
Exactly. It's the measure of inertia, resistance to acceleration. Heavy mass, or gravitational mass, is different. It's how strongly something feels the pull of gravity. It's the mass you use in Newton's law of gravitation.
And experimentally, people had tested this with incredible precision, even by 1923, and found
They are exactly proportional. For all intents and purposes, they are equal. A kilogram of feathers resists acceleration exactly as much as a kilogram of lead, and it feels the Earth's gravity exactly the same amount.
which suggests what? That acceleration and gravity are somehow linked?
That they might be two different ways of looking at the same fundamental thing. This is where Einstein's famous thought experiment comes in the elevator.
Right. Or maybe a physicist in a sealed box.
Yeah, the sealed box works perfectly. Let's imagine two scenarios. Scenario K, you're in a box floating freely in deep space,
Yeah.
far from any gravity, total inertial frame.
Okay. If I drop my keys, they just float there.
Right, force-free, no acceleration. Now, scenario K prime,
Yeah.
you're in an identical sealed box, but this box is being uniformly accelerated upwards by some external rocket, let's say at 9.8 meters per second squared.
Okay. Now if I drop my keys.
They appear to fall straight down to the floor of the box,
Yeah.
just like they would on Earth.
And if I stand on a scale in the accelerating box?
It reads your normal Earth weight. If you throw a ball sideways, it follows a parabolic path relative to the box.
Just like gravity.
Exactly. The profound conclusion Einstein drew is this. From inside the sealed box, there is no experiment you can do with matter or even light that can tell you whether you are in K prime, uniformly accelerating in gravity-free space, or if you are simply sitting still in an inertial frame that happens to be in a uniform gravitational field.
Acceleration perfectly mimics gravity. Or gravity perfectly mimics acceleration.
They are indistinguishable locally,
Yeah.
and if they're indistinguishable, maybe they are the same thing, viewed differently.
And that realization completely destroys the special status of the inertial frame, doesn't it?
It pulls the rug right out. If acceleration feels exactly like gravity, then what justification is left for saying that unaccelerated inertial motion is somehow more fundamental or preferred than accelerated motion? They're equivalent.
Which leads straight to the core principle of the new theory.
The general relativity principle. Any frame of reference, moving arbitrarily, accelerating, rotating, whatever, is just as valid as any other for writing down the laws of nature.
Wow. So finally, no physically preferred states of motion whatsoever. Complete democracy for coordinate systems.
That's the goal. But making that work physically requires a radical rethinking of geometry itself.
Because we already know from special relativity that motion affects measurements. Lorentz contraction, time dilation. If frames can move arbitrarily, things get really weird for rulers and clocks.
They do. If you imagine trying to set up a standard Euclidean grid, like rigid graph paper, in an arbitrarily moving or rotating system, the lengths and times get distorted. The concept of a rigid rod, and therefore Euclidean flat geometry, it just breaks down. It doesn't apply anymore.
So space isn't just a passive background stage anymore.
Not at all. This was the crucial leap for Einstein. The gravitational field isn't some force acting within space-time. The gravitational field is the curvature of space-time. And the metric, the way we measure distances and times, is also determined by that curvature. They are, as he says, different manifestations of the same physical field.
Gravity is geometry.
In a nutshell, yes. Gravity tells space-time how to curve, and space-time tells matter how to move.
Okay, let's try to get into the mechanics of how this is described mathematically. Because if space is curved, our usual XYZ coordinates don't really work anymore, do they?
Not globally, no. Einstein explains that while a large region of space-time might be curved, if you zoom in on any infinitesimally small neighborhood, like a tiny point environment.
Like looking at a tiny patch of the curved Earth's surface.
Exactly that analogy.
Yeah.
Locally, it looks flat. In that tiny region, you can always define a local inertial frame where, for that instant and that spot, there's effectively no gravity, and the laws of special relativity hold true, at least to a first approximation.
Okay, so locally flat, globally curved. How do you describe the whole curved thing then?
You need more general coordinates, arbitrary labels for points in space-time. These are the four-dimensional Gaussian coordinates, often written as 6 by $, by 2, by 3, by 4, 2, 1, where one is time and the others are spatial dimensions. They don't have to correspond to physical lengths or times directly. They're just labels.
And the thing that stays constant, the real physical measure, regardless of which weird coordinate labels you use, is the space-time interval.
Yes, the invariant space-time distance between two infinitesimally close events, usually written as $22. You can measure this 22 using physical rulers and clocks within that local inertial frame where things are momentarily flat.
Okay.
Now, when you write down the formula for this invariant 3D2 true using those general arbitrary Gaussian coordinates by CERN-Core 4, the equation involves a set of 10 functions. These are the famous jaw coefficients.
The metric tensor components. These sound important.
They are everything. These Young functions are what define the geometry. They tell you how to calculate distances and time intervals at every single point in space-time, given your chosen coordinate system.
Yeah.
They contain all the information about the curvature.
Wait, you said gravity is the geometry, so these jogging things must also be...
The gravitational field. That's the profound connection from the equivalence principle. The 10 GIP components simultaneously determine the metric, the geometry of spacetime, and describe the gravitational field relative to your chosen Gaussian coordinates.
Whoa. Okay, so unlike Newton, where gravity was a force acting in space, here the gravitational field is the structure of spacetime, encoded in these gigo numbers.
Precisely. The field equations of general relativity are equations that tell you how matter and energy determine these GO coefficients, how matter and energy curve spacetime.
And once you know the go together, once you know the curvature, that tells objects how to move.
Yes, the law of motion gets completely reframed. An object moving freely under gravity isn't being pulled by a force anymore. It's simply following the straightest possible path through the curved spacetime.
The path of least resistance, essentially.
Exactly. This path is called the geodetic line. It's the generalization of Newton's first law, or Galileo's law of inertia, to curved spacetime. Objects follow geodesics.
So, by 1923, when Einstein gave this lecture, how well was this radical new geometric theory actually matching up with observations?
It was doing remarkably well, but with one caveat he's careful to mention.
Okay, the successes first.
Well, crucially, GR reduces back to Newtonian gravity in the limits of slow speeds and weak gravitational fields. So it contains the old theory as an approximation, which is essential.
Good check.
And it made specific new predictions that were confirmed. The biggest one was explaining the weirdness in Mercury's orbit, the precession of its perihelion, which had baffled astronomers under Newtonian gravity. GR nailed the numbers.
Huge win.
And the other major confirmation was the bending of starlight as it passes near the sun. Eddington's expedition during the 1919 solar eclipse provided famous observational proof. Light follows the curvature of spacetime.
So, two big confirmed predictions. What was the caveat?
Einstein is very honest here. He notes that agreement with the predicted gravitational redshift of spectral lines was, in his words, not yet completely assured, however.
Explain the redshift again.
It's the idea that light climbing out of a gravitational field loses energy, shifting its frequency towards the red end of the spectrum. It's essentially a measure of gravitational time dilation. Time runs slower, deeper in a gravity well.
So they believed it happened, but the measurements weren't precise enough in 1923 to fully confirm GR's exact prediction.
That seems to be the situation. The qualitative effect was likely accepted, but getting the quantitative agreement was still experimentally challenging back then.
Okay. So general relativity arrives. It solves the physical relativity problem by eliminating preferred frames entirely. It largely satisfies the stipulation of meaning for space, time, and gravity by grounding them in the measurable geometry of spacetime. But as soon as this huge structure is built, Einstein immediately sees the next set of even bigger challenges looming. The work was far from over. Right, so GR handles gravity and geometry beautifully. But the universe isn't just curved spacetime, is it? It's got stuff in it, matter, and other forces, like electromagnetism.
Exactly. And this is where Einstein, even in 1923, runs headlong into the problems that would basically define the rest of his scientific life. The quest for unification.
How did he try to fit electromagnetism into the GR framework?
Well, mathematically, you could do it relatively easily. You could just take Maxwell's equations, which describe electricity and magnetism, and just sort of paste them into the GR structure. You assume they hold true in those little local inertial frames where spacetime is momentarily flat. You can even add electromagnetic terms to the main gravitational field equations.
Okay, so you can bolt the two theories together. But did that lead to a deeper understanding? Did it feel unified?
Not really. He says explicitly this combination had not given a satisfactory theory of matter. That was the sticking point.
Why not? What was missing?
To make the combined theory work, to account for how, say, electrons or protons generate both gravitational and electric fields, you still had to put matter into the theory by hand.
Like an ingredient you just add.
Yes. He called it an approximate phenomenological representation. You had to say, okay, assume there's a particle here with mass m and charge e, and then calculate its effects.
Instead of the theory predicting that such particles with those properties must exist as natural consequences of the underlying field structure.
Precisely. Matter wasn't emerging from the geometry. It was still something external you had to plug in. This really bothered Einstein.
And it links back to that stipulation of meaning again, doesn't it? If you're just defining matter phenomenologically, you haven't really given concepts like mass and charge a fundamental grounding in the theory itself.
You haven't. And worse, these plugged-in particles, like the electron, were typically modeled mathematically as points, singularities.
Right, points of infinite density and infinite field strength where the equations kind of blow up.
Yeah, that felt deeply unnatural to Einstein. He believed a truly complete field theory should describe everything, including particles, as smooth, continuous field configuration solutions free from singularities. No infinities allowed. That was a huge goal, and this combined approach wasn't getting there.
This problem with matter also connects to another deep philosophical issue he was wrestling with, inherited from Ernst Mach, right? The origin of inertia.
Ah, yes, Mach's principle or Mach's stipulation.
Yeah.
We talk about how Newton explained inertia as resistance to acceleration relative to absolute space.
Which fails the stipulation of meaning because absolute space is unobservable.
Exactly. Mach argued that inertia shouldn't be relative to imaginary space, but relative to all the other matter in the universe.
So the reason it's hard to push a bowling ball is because of the combined influence of all the stars and galaxies out there?
That's the essence of it. Inertia as a kind of acceleration induction. The resistance a body feels to being accelerated relative to the bulk mass of the cosmos.
Does general relativity support this idea?
It does, partly. GR does contain effects that look like acceleration induction. Inertial effects are linked to gravitational effect caused by distant matter in GR, so it points in Mach's direction. But Einstein notes that, according to GR's equations, this induced inertial effect from distant matter is incredibly tiny, far too small to be detected directly by any conceivable mechanical experiment back then.
So GR leans towards Mach, but doesn't fully implement his idea in a practical way.
Not quite strongly enough for Einstein's satisfaction at this point. And to make Mach's idea work completely, to ensure that the inertia of any object is entirely determined by the rest of the matter in the universe, Einstein felt compelled to make a huge assumption about the universe as a whole.
This is where cosmology comes in.
Yes, the cosmological dilemma.
Hmm.
To satisfy Mach's principle rigorously and to avoid certain mathematical issues with infinite space in GR, Einstein proposed that the universe must be spatially finite and closed, like the surface of a sphere, but in higher dimensions.
A universe with a finite amount of space, but no edge.
Exactly. This allows for a universe filled with a finite average density of matter everywhere, which mathematically helps tie inertia fully to that matter content, just as Mach wanted.
But making the universe finite like that, it came with a pretty big cost, didn't it? Something Einstein wasn't happy about.
A huge cost, philosophically. To make his equations describe a static, finite universe, remember this was before Hubble discovered the expansion, he had to add an extra term, the infamous cosmological constant.
Lambda, the fudge factor.
Pretty much. It acted like a kind of cosmic repulsion to counteract gravity and keep his finite universe from collapsing in on itself. But he admits right here in the lecture that this term had no experimental basis whatsoever and wasn't logically required by the rest of the theory.
So he introduced it purely to make the finite universe model work and satisfy Mach's principle.
Yes. And that deeply violated his own stipulation of meaning, introducing a fundamental constant without observational backing, just for theoretical or philosophical tidiness. He calls the whole finite universe solution not completely satisfactory for the time being. You could feel his discomfort.
That tension between the math, the observations, or lack thereof, and the philosophical drive really pushed him towards the ultimate goal, didn't it?
Absolutely. The search for a unified field theory.
The Holy Grail.
The Holy Grail. He just couldn't accept aesthetically or logically that nature would have two fundamental forces, gravity and electromagnetism, described by completely separate mathematical structures, one based on geometry, the other based on Maxwell's equations.
He felt they had to be just different aspects of one deeper underlying field.
Yes, a single, unified field. And the way forward, he thought, was to generalize the geometry even further.
GR already seemed pretty general with its curved spacetime.
GR is based on what's called Riemannian geometry, which starts with the concept of distance, the metric 2 parts of 2. The idea, explored by mathematicians like Levi-Civita and physicists like Weil and Eddington around that time, was to build physics on an even more fundamental geometric concept, a fine correlation.
The fine correlation, that sounds abstract.
It is. Instead of starting with how to measure distance between points, the metric, you start with a rule for how to transport a direction, a vector, parallel to itself along an infinitesimally short path. It's the rule for parallel transport.
Okay. How does that help unify things?
Well, a Riemannian geometry implies a specific rule for parallel transport. But you can define parallel transport rules that are more general than those implied by Riemannian geometry. These more general affine connections have more mathematical freedom, more components in them.
Ah, so the hope was that those extra mathematical components in this more general affine geometry might naturally correspond to the electromagnetic field.
That was exactly the hope. That you could find a simple, elegant set of field equations based on this affine structure, and out of those equations would pop both the gemor of gravity and the fields of electromagnetism, all from one unified geometric foundation.
What guided the search for the right equations in this more general framework if it's not just Riemannian geometry anymore?
This is where it got tricky. Einstein admits the main guide was mathematical simplicity of the resulting differential equations, which he concedes is not free from arbitrariness. He was betting on mathematical beauty and elegance to point the way because experimental guidance was lacking.
A risky path.
Very. And he laid out two crucial tests for any proposed unified theory to be considered successful.
What were they?
First, it had to predict new physical connections. It couldn't just repackage gravity and electromagnetism. It had to show some deeper link or predict new effects. And second, absolutely critically, it had to solve the singularity problem. It had to represent the fundamental particles of matter, like electrons, as smooth, finite field configurations, solutions free from singularities.
If it couldn't get rid of those infinite points, it wasn't the true theory.
Exactly. That was a non-negotiable requirement for him.
And then, casting a huge shadow over this whole ambitious project of unifying the classical fields, there was the other revolution brewing in physics,
The elephant in the room, quantum theory.
which he calls the most profound physical problem of the present time.
And he knew it was a massive challenge to his entire program. Because relativity, both special and general, was fundamentally a classical theory. It dealt with continuous fields, smooth space-time, deterministic laws.
Whereas quantum mechanics described the world as fundamentally lumpy, probabilistic.
Discrete energy levels, quantized momentum, particles behaving like waves, inherent uncertainty. It was a completely different conceptual world. And relativity, he admits, has so far proved ineffectual in making sense of any of it.
It's like trying to mesh gears from two completely different machines, one smooth, one jerky.
A perfect analogy. How do you reconcile the smooth geometric description of gravity with the fundamentally discrete and probabilistic nature of the matter and energy creating that gravity? That was the huge unresolved tension, clear as day in 1923.
A tension we're still grappling with today, really.
Absolutely. The quest for quantum gravity is the direct intellectual descendant of the problems Einstein was outlining here.
But even facing that enormous quantum challenge, even acknowledging that his specific field equations for GR might need radical changes, he makes one final, really confident prediction.
He does. He predicts that even if the fundamental equations change drastically because of quantum theory, the core relativity principle itself will not be relinquished.
The demand for no preferred frames. The idea that the laws should look the same regardless of your state of motion or your coordinate system.
That principle of maximal symmetry, of general covariance, he believed that was a permanent fixture, a limiting law that any future theory would have to respect. For him, it wasn't just a feature of GR, it was a fundamental logical requirement for any sensible description of nature. Hashtag tag outro.
Wow. What an incredible journey through Einstein's mind in 1923. This deep dive really lays bare the entire intellectual arc, doesn't it?
It really does. From that initial philosophical insistence on meaning, the stipulation of meaning,
Right, demanding that concepts connect to observables,
through using that to dismantle the classical inertial frame, which then forced special relativity,
which still wasn't enough because it kept preferred frames.
leading finally to the geometric insight of general relativity, where gravity is space-time curvature.
But then immediately seeing the next frontier, the need to unify gravity with electromagnetism, to understand matter fundamentally, get rid of singularities.
And all of this happening with the storm clouds of quantum theory gathering on the horizon. It's amazing how clearly he saw the entire landscape of 20th and even 21st century physics laid out before him.
What really strikes me is his intellectual honesty. Even at the height of his fame, he's pointing out the flaws, the compromises, like the cosmological constant, the places where his own theories fall short, like with matter and singularities.
Yeah, there's no sense of mission accomplished here at all. He knew exactly where the deep logical weaknesses remained, and pinpointing those weaknesses basically set the research agenda for physics for the next 100 years.
And that foundational principle we started with, the stipulation of meaning, that seems like the engine driving the whole process.
I think it was. That relentless demand for logical clarity, for grounding physics in what can actually be observed and measured, that's what forced the revolutionary breaks with classical intuition about space and time. He wasn't just playing with math. He was demanding that the math mean something physically unambiguous.
So, let's leave our listeners with a final thought, trying to connect Einstein's struggle back then to our world now.
Okay.
If Einstein, a century ago, had to fundamentally question things as basic as simultaneous time or rigid measurement, because they weren't unambiguously definable or observable. What about today? In our incredibly complex, information-saturated world, what seemingly obvious or absolute concepts might be the weak points, the shaky foundations of our current thinking?
That's a great question. Think about things we take for granted, like maybe the objectivity of data processed by complex algorithms, or perhaps the very meaning of causality in globally interconnected systems, or even consciousness itself.
Are we always applying that Einsteinian rigor, asking if these concepts truly correspond to unambiguous observable facts? Or are we sometimes building on foundations that might be just as purely imaginary as absolute space seemed to him?
Applying that level of critical self-reflection, that deep insistence on meaning and logical coherence that Einstein exemplified, perhaps that's the most important takeaway from revisiting this moment in physics history.
A challenge for all of us. Well, thank you for joining us on the deep dive.